we carry on from where we got to on Thursday. So we're still talking chemistry, still looking at equilibria, but we're looking at gas equilibria now. So we obviously, we looked at on Friday gas equilibria and calculating partial pressure. So what we're going to look at now is calculating the equilibrium constant for gas phase. So when it's equilibrium constant for anything that's not gas phase, it is Kc. But when we're looking at equilibrium constant for gas phase reactions, we call this Kp. And if you look at this reaction equation, it looks almost identical, but obviously this time we've got gaseous state symbols next to everything. So AA plus BB can go to and back from CC plus DD. So for this general equilibrium, Kp is given by this. So it's almost exactly the same, but we have this P here. Show you, we've got this P here in front of everything that we didn't have before. And that's for the pressure, that's identifying the partial pressure that we're going to look at. So obviously we calculated partial pressure on Friday, Thursday, and now we actually need to use the partial pressure for the general equilibrium equation. So yeah, apart from that, it's almost exactly the same. So Kp equals PCC PDD over PAA PBB. So where PA means the partial pressure of species A, so then partial pressure of species B, C, partial pressure of D. So like Kc, we have to calculate the units for Kp for each reaction. And this time, obviously, our units will be different because we're talking about pressure. So we're looking at kilopascals. So again, for gas phase equilibrium, we've got a different one here. We've got A plus 2B goes to C plus D. So our equilibrium constant, Kp, is given by this. So our partial pressure of species C multiplied by a partial pressure of species D is then divided by the partial pressure of species A and the partial pressure of species B squared, so to the power of 2. So we're going to do exactly the same as we did before. I'm going to calculate units before. So the units are in kilopascals, and we're just going to cancel them out. So we can cancel this one and this one, and we can get rid of the 2. So we just have that there. Now remember, because that's on the bottom, we need to flip it to the top. So it'd be kilopascals. Oh, sorry, that was not helpful, but I've now wrote all over it and they've done it a different way. Pen, eraser, 1 over kilopascals. Obviously there, then we have it to -1, because the kilopascals are on the bottom, then obviously we need to invert the equation. So, oh, I wanted to refresh this, 1 second. Let me just do that. Let's just refresh this page because I've already, for some reason, it's got questions already done. Calculated partial pressure. We've done that. Equilibrium constant. Units of Kp. Is this the one we're on? Kp expressions and units. Here we go. So let's go through these questions. Kp expressions and units. So what is the Kp expression for this equation? So our equation is A plus B goes to 2C plus D and then back again. So let's write this out. And then obviously you can then pause this and then choose an option if you want to later. But yeah, let's go at this one. So let's put this here. We've got Kp equals, and obviously we're going to have the bottom half on the top. So we have partial pressure of species, C, 2 lots of species C, so that's 2, and then we'll have partial pressure of species D. Bottom, we're going to have partial pressure of species A and partial pressure of species B. Let's have a look on the left. Well, which one matches that? That's our top one. There. So, let's move on to the next question. So what is the KP expression for this equation? So let's do exactly the same thing again. Let's write the whole thing out. So we've got KP equals partial pressure of NH3 power of 2, partial pressure of N2, partial pressure of H2 to the power of 3. And then we've got the power of 3 and the power of 2 because we've got 3 lots of hydrogen, 2 lots of ammonia. So that will match with our top one again. Yes, it will match with our top one again. This time, what are the units of KP in this expression? So let's just write out the units and cancel them out. I know you could probably work this out, but let's just go through it slowly, work it out. So KPA, KPA over KPA, KPA squared. So got that one left over, so that'd be 1 over KPA. Swap them around, which means we've got kilopascals 1. So we've got kilopascals to the power of -1. Fantastic. So let's have a go on the next one. So what are the units of KPB for the following reaction? Let's do exactly the same thing again. Let's write out KP here. KP, got 2 HI up at the top, so we're going to have kilopascals to the power of 2, because we've got 2 there. We've got H2 and I2, so it's just kilopascals multiplied by kilopascals. They cancel each other out, so we will have no units. I mean, again, it won't be moles because this is KP. If it's KC, we'd be looking at moles, but we're not. So it'll be no units because they cancel out anyway. And then finally, for this set of questions, what will the units be? What will the units of KP be for the following reaction? So let's write this one out again. So we've got KP, KP equals kilopascals for NH3 power of 2, KPA, KPA power of 3. Okay, so that can cross out with that, leave them there. So they would be KPA minus 2. On the bottom, we need to move them to the top. Okay, so that's how we calculate our units. That's how we calculate, put them into the equation. Let's actually look at calculating kilopascals, equilibrium constant for partial pressure now. Okay, so we're calculating equilibrium constant of partial pressure. So we're going to look at this example. So we've got 2 H2O plus CO, reversible reaction of CH3OH even. So we've got 2 moles of hydrogen and 1 mole of carbon monoxide, and they were mixed together. At equilibrium, the mixture contains 0.175 moles of CH3OH. And what we're going to do is we're going to look at the animation and find out how we calculate KP. So I'm going to break it down into stages. So step 1, the first thing we want to do is we want to work out our number of moles of each species at equilibrium. So what we're going to do is we're going to use the ratio of reacting species to work out how many moles have reacted. So let me just make this bigger. Pause that a minute. Let's go back here. So we've got 2H2 plus CO, making CH3OH. So lots of nice quiet things lots of people like to do is make a table for this. On this table, we've got each species, and then we've got moles at the start of reaction, in the middle, number of moles that have reacted, and then at the bottom, number of moles at equilibrium. So we're going to put in our ratio of moles at the top. So it's a 2 to 1 to 1 ratio. We've got 2 lots of H2, 1 lot of CO, and then 1 lot of CH3OH. So moles at start of reaction, well actually at start of reaction we've got none of this, got 2 moles of H2 and 1 mole of CO. Number of moles at equilibrium you will be given generally for CH3OH, and that is 0.175. So what we're going to do with that is we're then going to look at how many moles have reacted so far. So we're going to use our ratios that we've spoken about. So we've got our 2 to 1 to 1 ratio. So our number of moles that have reacted for carbon monoxide will be exactly the same as our number of moles of equilibrium of our CH3OH. So what should happen is, there we go, 0.175 multiplied by 1, because that is our ratio 1 to 1. Our ratio for hydrogen is obviously a 2 to 1. So we're just going to multiply 0.175 by 2. So we should get 0.350. And that's because we've multiplied that number there by 2 because of ratio 2 to 1 to 1. Then, using this, we can then work out our number of moles at equilibrium. So let me just go back a bit. So we had 2 moles to start off with. 0.35 moles have reacted. So you're going to do a simple equation of 2 minus 0.35, which then will give us 1.65. And do exactly the same thing for CO. So we had 1 mole. We're going to take away 0.175 moles, which will leave us with 0.8250 moles at equilibrium. So at the moment, at equilibrium, we've got 1.65 H2, 0.825 moles of CO, and 0.175 moles of CH3OH. That's the first part. Okay. Then what we do is we go on to step 2. So step 2, we're going to work out our mole fraction. So this is very similar to when we were doing equilibrium constant for anything but gases. And so we're going to work out our mole fraction of each species from a number of moles calculated in step 1. So let's have a quick look at this. Let's make this bigger. Oops, let's go back. No, go back. Right. Right, so this is where we were from step 1. We've worked out how many moles we have at equilibrium. What we need now is a mole fraction equation. So our mole fraction equation is mole fraction of species A equals our moles of A divided by our total number of moles. So we can use another little table to help us with this. So we've got our number of moles from equilibrium from before. So for 1.65, 0.825 and 0.175 carried over. Then we have our total number of moles in total. So we've literally just added those 3 numbers together. So our total number of moles at equilibrium is 2.65. So then we just want to work out the mole fraction. So to work out the mole fraction, we're literally just going to do for example, 1.65, and we're going to divide that by 1.65. I'm going to divide that by 2.65, and that should give you 0.623. You do the same for CO. We'll do 0.825 divided by 2.65, and we'll give us 0.311. And then finally, 0.175 divided by 2.65 will give us a mole fraction of 0.066. So that is our mole fractions that we have calculated. So first step, we've worked out how many moles at equilibrium. Second step, we work out our mole fractions. Now what we're going to do is step 3. In step 3, we're going to now work out our partial pressure of each species from our mole fractions. So this is where it's a bit different because we're dealing with gases. So we need to work out our partial pressures each species from our mole fraction. So, oops, this is where we were at the end of the last step. And step 2, we've got our moles at equilibrium and our mole fraction. And then just basically going to add on an extra little bit to our table. And we're going to add on a partial pressure section. So a reminder of the partial pressure equation. So partial pressure of species A, for example, so PA equals our mole fraction of that species multiplied by our total pressure. Our total pressure for this one is 1.75 times 10 to the power 4 kilopascals. So if we want to calculate the partial pressure of hydrogen, we're literally just going to take 0.623, multiply that by 1.75 times 10 to the power 4, and that will give us, 10,902.5. For carbon monoxide, it's 5,442.5, and CH3OH is 1,155. And our total obviously is still going to remain the same at this point. We don't need to do anything with our totals there. So that's our partial pressures. So that's sort of the last stage before we have to really can then input it to calculate it. So we've worked out number of moles equilibrium, our mole fraction, and then our partial pressure. Now, step 4, we're going to write down our expression for Kp. So Kp, I'm actually going to just do this one here. Can I get it? Oh, I can't see it. Yes. So Kp, equation for Kp in this situation would be Kp equals partial pressure of CH3OH over the partial pressure of H2. I can remember, I'm sure that was squared, and the partial pressure of CO. So that's what that should look like. What we should see, if I click mouse, press play. There we go. Something exactly the same appears. So we've worked out the equation for equilibrium constant of partial pressure. So then the final steps is actually just inputting these numbers into that equation. So we've got that equation that we've just worked out, and now we're just going to insert our values. Oops, would help if I made that bigger so you could see. And so that's our equation we just worked out. We're going to input our values. So obviously our value on the top will be 1155. Value at the bottom here will be 10,902.5 to the power of 2, and then 5442.5. So this is what you should get. I'm going to run this through the calculator, but before we do that, let's just have a quick look at what our units will be. So this unit, this one, we'll cancel out with this, so we'd still have that there. So we're going to have kilopascals to the -2 will be our units. Clear all my drawings. Let's double check. So our answer should be, run through, 1.785 times 10 to the -9 kilopascals to the -2. And that would be our equilibrium constant for this question. So what we're going to do now is we're going to sit and we're going to work out some equilibrium constants for a few more. So we've got some questions here. So calculating equilibrium constant. So I'm going to basically just talk it through with you on here. I'm going to actually probably get a whiteboard up in a second actually and show you on there and then go through the answer here. So question 1, we've got 2 HI going to H2 plus I2. So 1 mole of HI was left to decompose at 100 kilopascals. At equilibrium, we have 0.778 moles of HI. Remained, what is the value of Kp? So what I'm going to do is I'm going to actually get the whiteboard up more. So I'm just going to go through it here. So we've got this as our equation. We've got 2HI, H2 plus I2. So let's have a look at those units. So at the start, we've got, well, if we have 1 mole of this, at equilibrium, we were told it would be 0.778. So that's what we've got at the start, that's what we've got at equilibrium. We want to know how much has actually reacted. Okay, so really nice and simple. We're going to do 1 minus 0.778. Get that, that would give us 0.222. So that's how many moles we had at the start, at equilibrium, and how many reacted. So here we have it at a ratio of 2 to 1 to 1. Okay, so if we just talk this bit through here, so we know 2 moles of HI react to make 1 mole of H2 plus 1 mole of I2. Therefore, 0.22 divided by 2 equals 1.111 and 1.111. So if we did this as the start thingy table, we have 0, 0, 0 there, 0, 0 reacting there, and we have 1.111 and 1.11. So that is how many moles we have at equilibrium here. I'm going to change my pen colour now because we're going to now work out our mole fractions. So first of all, we need to work out our total moles in our equation. So our total moles in our equation, so I'm going to pop total moles here. Total moles, that would be 0.778 plus 0.111 plus 0.111, and double check this on the calculator, 0.778 plus 0.111 plus 0.111 equals 1. So our total number of moles is 1. So for our mole fractions, so our mole fractions of HI, our mole fractions of H2, and our mole fractions of I2, we're going to do, for example, that should be HI, sorry. HI, we're going to do 0.778. I'm going to divide that by 1. So obviously we're going to have 0.778. 0.778. H2 would do 0.111 divided by 1, so it would be 0.111, and the same for I2. So now we just need to calculate partial pressure. So if you can remember from earlier, to calculate partial pressure, we're going to multiply our mole fraction by our pressure total, our P tot. Our total pressure for this question was 100 kilopascals. Let me just stick that here. 100 kPa is our P tot. So we're going to multiply all of these by 100. So multiply them by 100 times by 100 times by 100 to get our partial pressure. So then we will get partial pressure of 77.8, 11.1 and 11.1. Now we want to get the calculation. So we've got Kp equals H2, partial pressure of H2 plus the partial pressure of I2 over the partial pressure of HI to the power of 2. So let's insert our values into this. So Kp equals, what's our partial pressure of H2? Partial pressure of H2 is 11.1 multiplied by 11.1 over 77.8 power of 2. Let's just quickly work out units before I put that through a calculator. Let's double check our units. So we've got 2 here. The units are going to cancel out. So our unit should then be, or we should then get 0.0204. And that is our equilibrium constant. So if we go back and find it, here we go. Screen sharing, let's go back to what I want to screen share. They'll all learn. share. Here we go. I said 0.0204. Obviously, there's no units because they've all cancelled themselves out. So we're on 0.0204 here. And so again, we've calculated the number of moles of each species. We then calculated the equilibrium, then we've calculated the total number of moles present at equilibrium. We then calculated the mole fraction of each species, and then we have calculated the partial pressures of each species at equilibrium, wrote the expression for Kp, and then substituted our values to calculate Kp. So it is quite a long process. I'm going to go through one more example with you. So we've got PCl3 plus Cl2 goes to PCl5. So we've got 0.546 moles of PCl3 and 0.373 moles of Cl2, and they were heated. At equilibrium, there was 0.178 moles of PCl5. Our total pressure is 225 kilopascals. What is our equilibrium constant? So let's go back to whiteboard. New page. Let's put this equation at the top. So we've got PCl3 plus Cl2 goes to PCl5. PCl5. Okay, so at the start, we're going to basically put this into a table for now. Start reacted equilibrium. So at the start for PCl3, we have got 0.546 moles. For Cl2, we have got 0.373, and we're also told at equilibrium we have 0.178 moles of PCl5. If we look at our ratios, we have a ratio of 1 to 1 to 1. Oops, that's annoying. 1 to 1 to 1. Undo that now. So 1 to 1 to 1. If that is how much we've got at equilibrium there, the same amount will have been reacted, will have been used up for species A and species B. So the amount reacted would be 0.178, and the amount reacted here would be 0.178. So then to work out how much we would have at equilibrium, we would do 0.546 minus 0.178. So at equilibrium, PCl3, we would have 0.368 moles. Cl2 would do 0.373 minus 0.178, and that would give us 0.195 moles at equilibrium. We then need to work out our total moles at equilibrium. So I'm just going to put my total here. So we would do 0.368 plus 0.195 plus 0.178, and that will give us 0.741. Now we need this mole total to work out our mole fractions. So we're going to do mole fractions. I'm just going to change this color. So we're going to do mole fractions. And we're going to do a mole fraction of Cl3, Cl2, and PCl5. So our mole fraction of PCl3 would be 0.368 divided by 0.741. And that will give us an answer of, I'm just going to put all the equations here. That would give us an answer of our mole fraction. Actually, I'm going to write mole fraction here. That would give us 0.497. This one we're going to do 0.195 and divide that by 0.741, and we will get a mole fraction of 0.263, and then finally 0.178 divided by 0.741. would give us a mole fraction of 0.246. We then need to calculate partial pressure. Remembering that partial pressure is our mole fraction multiplied by our pressure total. Now, our pressure total from this question was 225 kilopascals. So we're going to multiply all of these numbers by 225, 225, 225 to give us our partial pressure. So that would be 0.497 multiplied by 225 would give us 111.8. 0.263 multiplied by 225 would give us 59.2. And then finally 0.246 multiplied by 225 would give us 54. Now we can put this into the equilibrium constant equation. So let's get that up quick. So we've got Kp would equal partial pressure of PCl5 over partial pressure of PCl3 and the partial pressure of Cl2. Working out our units, it's going to cancel out. So we've just got, so our units are going to be kilopascals minus 1. So let's put in our values. So our partial pressure for PCl5 is 54. So it will be 54 over 118 multiplied by 59.2. And that would give us an answer of 8.10 power of 10 to the power of minus 3 kilopascals to minus 1. And that would be our answer for that one. That would be our equilibrium constant. So if we go back to the question, there we go, 8.16 times 10 to the minus 3. So that is gas equilibrium constant. What we're going to have a quick look at now, close that one. It's not that, is we're going to look at equilibria 3, which is industrial equilibria. So for industrial equilibria, this one's a bit more fact-based rather than mathematical-based. So the sort of stuff that you have to learn for this is rather than learning different formulas to calculate this, we're sort of just learning some facts for this. So we're going to understand how to make ethanol from ethene, understand the hydration of ethene, understand the formation of methanol, and then understand what carbon neutral activities are. So traditionally, we make ethanol by fermentation of biomass using yeast. So ethanol is an alcohol. We can ferment any sort of biomass using yeast and we can produce ethanol. However, it's not suitable for meeting industrial ethanol needs in countries, for example, like UK, the USA, China, etc. We just need too much ethanol, industrial ethanol, to basically go through that fermentation process. So we can use something else. What we do industrially is we make ethanol and we manufacture it by hydration of ethene. And ethene is a product of cracking crude oil. So if you think back to GCSE and you've done cracking and crude oil, ethene is a product of crude oil, of cracking crude oil, and we can make ethanol by hydrating ethene. So the forward reaction is exothermic and it is catalyzed by phosphoric acid. So we have ethene plus water and we get ethanol, and obviously above forward our equilibria signs we can then also put in phosphoric acid because that is going to be our catalyst. Oh, right, that's Go back to the beginning of that. Right, let me go back to the beginning. Yeah, here we go. So we're going to look at the hydration of ethene. So we're going to look at something called Le Chatelier's principle. And what Le Chatelier's principle says is that increasing of the proportion of one of the reactants will in turn increase the proportion of ethanol formed. So steam is cheaper than ethene, so economics suggest using excess steam. So we're just going to talk through that now. So here we go. Ethene, water, phosphoric acid, ethanol. Proportions. So these are proportions of our reactants. So we've got ethene and steam, if we have them equal. If we increase steam, we actually get an increase in ethanol being produced. So steam being our water. But when we choose steam, because steam is a lot more economical than providing more ethene. So that is one way that we can increase production of ethanol. Now it's hydration of ethene. So the problem of using excess steam, and there is a problem, is that the phosphoric acid catalyst that we use is water soluble. So we increase steam, the catalyst is washed away, but without a catalyst, the rate of reaction becomes very slow. So we would say that this increases, but this is phosphoric acid. Just said phosphoric acid is water soluble. It will wash away that increase of steam. So what actually happens to our proportion of our reactants is our rate of reaction really slows down. So that's we might get this increase that we see here. It happens a lot slower. So in practice, a small excess of ethene is used, and then this unreacted ethene is then separated and recycled to reduce wastage and unnecessary expense. So actually what we really do is we use slightly more ethene to get a larger yield of ethanol, and then we separate and recycle that ethene to use again. So the forward reaction is exothermic, so it's favoured by low temperatures. However, at low temperatures, the rate is so slow, the reaction takes a long time to reach equilibrium. So we can show you by this image here. If we decrease temperature, we get higher yield, but it is very slow. So a compromised temperature of 570 Kelvin is used. Why we do this is because at this temperature, the proportion of ethanol at equilibrium is similar than that at lower temperatures, but we get to equilibrium a lot more quickly. So if we were happy to wait around for ages, we could have a really low temperature and have a really high yield. But it takes a long time, so it's actually not that worthwhile. So we've actually said compromise, 570 Kelvin's better, because we get a similar amount of ethanol here, but it's happening a lot quicker. So we call that our compromised temperature, 570 Kelvin. So hydration of ethene still. The equation shows that in the forward reaction, 2 moles of gas form 1 mole of gas. Le Chatelier's principle suggests that increasing the pressure will increase the proportion of ethanol. So we've got 2 moles to 1 mole, we increase the pressure, we increase our proportion of ethanol. And then finally, issue with high pressure is it's really expensive to produce. And ethene has a tendency to polymerize at high temperatures. So again, we don't go with the highest pressure possible. So we go with a compromised pressure of 6,000 to 7,000 kilopascals. So summary, we have compromised conditions, and we use these in the hydration of ethene. They do not provide the they don't provide our high yield at equilibrium, but they are the best conditions when other factors are considered. So things like a catalyst, the speed of a rate of reaction, the price of it. So our conditions are, we have a phosphoric acid catalyst, we have a very small excess of ethene because we can't have an excess of steam because that will wash away our catalyst. We have a compromised temperature of 570 Kelvin because actually whilst we can get a higher yield with a lower temperature, the reaction takes a very, very long time to take place, so it isn't very economical. So they have a similar yield, slightly less, but it's similar. And then we go with the pressure of 6,000 to 7,000 kilopascals, because a high pressure creates a higher yield, but high pressure costs a lot of money, so we go with that compromise pressure. So we're going to go with a, oh, all right, I need to restart that because for some reason it's decided not to remember. Decided to remember I've already done it once, which is annoying. Industrial equilibria, yeah, we want true or false. Where's that gone? Hydration of ethene, true or false? So ethene is obtained from cracking. Yes, it is. That is true. The phosphoric acid catalyst increases the percentage of ethanol formed at equilibrium. True. High pressure favors more ethanol, but is expensive to maintain. That's false. Unreacted ethene is separated and recycled. True. And a high temperature leads to a fast reaction and a high yield at equilibrium. So we would say true because it doesn't have the I can't say highest today, highest yield, but it has a very fast reaction, so that's a lot better. So, yeah. There we go. Right, so what we're going to do now is we're going to look at methanol. So methanol is an important chemical used in the manufacture of other chemicals. Methanol is made industrially by the reaction of carbon monoxide and hydrogen. So we have carbon monoxide plus hydrogen and we make methanol. So we had a little look at this actually earlier when we were doing our equilibrium constants. So a mixture of copper, zinc oxide and aluminium oxide are used as our catalysts. The mixture of carbon monoxide and hydrogen is called synthesis gas, and it is made from methane and water by a process called steam reforming. So carbon monoxide, so methane and water, we make carbon monoxide and hydrogen. So that's our synthesis gas, and we get that from steam reforming. So formation of methanol, we're going to look at the conditions. So methanol can be produced by reacting carbon monoxide with hydrogen. So reaction conditions used are not those that may be expected. So formation of methanol. Our Ford reaction is exothermic. So again, like the formation of ethanol, it is favoured by lower temperatures. However, at low temperatures, the rate is really, really slow. So the reaction takes a long time to reach equilibrium. Low temperature, we get a high yield, but then it takes ages. High temperature, lower yield, but doesn't take so long. So we come up with another compromised temperature. This time it is 520 Kelvin. And this temperature, the proportion of methanol at equilibrium is smaller than at lower temperatures, but equilibrium is reached much, much more quicker. So we go with this compromised temperature because economically it's more viable. So our equation shows that in the Ford reaction, we have 3 moles of gas, we've got 1 mole of carbon monoxide, 2 moles of hydrogen, and form 1 mole of gas. Therefore, if we use Le Chatelier's principle, this suggests that increasing the pressure will increase the proportion of methanol. So we've got methanol at the end. If we increase our pressure, our proportion of methanol should increase. However, High pressure is really expensive to produce, so we go with a compromise pressure of 5,000 to 10,000 kilopascals. So in summary, our compromise conditions are used in the formation of methanol. They do not provide our highest yield at equilibrium, but they are the best conditions when we consider other factors such as economics. So our conditions are, we have a catalyst made up of copper, zinc oxide and aluminium oxide, a temperature of 520 Kelvin and pressure of 5,000 to 10,000 kilopascals. So ethanol and methanol can be used as liquid fuels. So for example, for specially adapted cars. Methanol produced from carbon monoxide and hydrogen can be a carbon neutral fuel. And a reminder, so a carbon neutral activity is one that has no net annual carbon greenhouse gas emissions to the atmosphere. So greenhouse gas emissions are a major cause of global warming. Aiming for carbon neutral status is in one way in which industries can try to reduce their impact on the environment. So are these statements about making methanol true or false? So methanol is made industrially from carbon dioxide and water. Well, that was false because it was carbon monoxide. A mixture of platinum, zinc oxide and aluminium oxide is used as catalyst. That is true. No, sorry, it wasn't true, that was false. The reaction used to produce synthesis gas is called steam reforming. That is true. And at low temperatures, the reaction is slow to reach equilibrium. True. And then finally, methanol is always a carbon neutral fuel, whatever method is used to produce it. Now, I feel like the answer is false there. It can be a carbon neutral fuel, depending what method we use. So that is the end of, I'm just going to stop recording now.